So let's start really simple. We can talk about mass in terms of the everyday experiences we have with mass. Whatever mass is and wherever it comes from, in the end, it's got to be something that we believe successfully describes these incredibly normal experiences. And when it comes to mass, there's really only two experiences that matter. The first experience is called inertia, and that's the feeling that something is resisting you when you push on it. One way we can characterize inertia is to say that massive objects just don't want to accelerate. We use the label mass to quantify the degree to which they don't want to accelerate. The second experience we relate to mass is gravity. We can think about this kind of experience in terms of how much effort is required to lift something, or how heavy something is. Alternatively, when we drop a massive object in a gravitational field, it will fall. In some ways, we might characterize gravity in the opposite way that we characterize inertia. Massive objects in a gravitational field want to accelerate. In fact, it requires effort in order to prevent them from doing so. Interestingly, the same concept of mass can be used to quantify this seemingly opposite experience. Because the experience of mass is so normal, we don't really appreciate just how weird that experience is. If we want to start seeing that weirdness, rather than describing inertia in terms of resistance, or how hard it is to move an object, we should describe it in terms of a force, a resistive force that the object actively generates when you attempt to accelerate it. Similarly with gravity, we could describe an active force generated by the object in order to push it in the direction of the gravitational field. In order to see just how weird these forces are, we'll set up a little thought experiment where we try to describe these forces without using the concept of mass. In the same way that ancient Greeks might have tried to describe lightning without making an appeal to Zeus, we are going to attempt to describe how we might get the experiences we associate with mass without appealing to mass. In short, we are embarking upon a mission to get mass from no mass. To get started, we will envision an empty, massless box. We are going to put something inside of the box in order to recreate the experience of mass. So what do we put in there? If mass can be described in terms of active forces, we can think of whatever is inside of the box as something that creates a force. For now, let's envision a small conceptual rocket. In order to recreate the experience of inertia, the rocket will produce a force whenever someone pushes on the box. One way you might set that up is to give the rocket an accelerometer, and when the accelerometer detects a push, the rocket fires a reverse pulse proportional to the push. The accelerometer should work just fine as a gravitational field detector, so the rocket will also create a thrust in the direction of the field. In the end, we'll have a box where if we push on it, it pushes back, in a way that resists acceleration, just like inertia. If we drop the box, it will fall, or if we lift the box, it will be heavy, just like gravity. What's really surprising here is that the behavior of the rocket inside of the box would actually need to be really sophisticated, not to mention challenging at least our classical notions of conservation of momentum in order to truly recreate the experience of mass. So we know it really isn't a rocket inside of the box, but whatever we put in the box should behave like that rocket. So what do we put in there? Einstein gives us a little clue here. The famous equation E equals mc squared relates energy to the mass of an object at rest. So we know that whatever is inside of the box has energy. But there's another subtle clue present in this equation. E equals mc squared is specifically referring to a massive object at rest. I think it's an important question to think about what it really means to be at rest. In the case of our massless box, let's just say that being at rest means that the box isn't moving and the energy inside of the box isn't leaving the box. Even if the energy is moving inside of the box, the fact that it doesn't leave the box gives us at least one sense to think of that energy as being at rest. So, our two requirements for describing mass are, 1, talking about what kind of energy is in the box, and 2, talking about how that energy doesn't leave the box. In order to resolve the picture of what's happening inside of the box, we now have a new question. What is energy? So all modern explanations of mass point out that mass is just energy. But those explanations usually stop unsatisfiably short at explaining just exactly how it is that energy ends up creating these common experiences we have with mass every single day. Throughout the history of physics, mass has been taken as this axiomatic thing that just is. Energy, on the other hand, is something that we've been trying a bit harder to understand. So what is energy? When talking about energy, we often talk about the agents which carry energy, and this involves two fundamental ideas. Energy can be described as a property of particles or a property of waves. So, if we want to put energy in our box, then we'll need to put some particles or some waves into the box. Now, there's been a very long-standing debate going back centuries about the relationship between particles and waves. This debate got some new fuel in the early 1900s when we started seeing things that we generally thought of as particles exhibiting wave properties, and vice versa. Now, I'm not going to resolve this debate in this video, but I will say that I'm personally persuaded by the idea that what we've always meant when we referred to particles was just idealized wave behavior. That means that any property we may have ascribed to particles, including mass, can also be ascribed to waves. Perhaps by the end of this video you will agree with me, but in the meantime, one thing that we can say for sure is that we don't have to pick between particles and waves, because according to our modern understanding of that relationship, whatever is inside of the box likely will exhibit properties from both of those classes. Now, our program here is to obtain mass from no mass. This means that whatever we put in our box shouldn't have mass to begin with. Lucky for us, such an object exists in abundance. An object which has no mass, which carries energy, and exhibits both particle and wave properties. This object is called a photon. In other words, we're going to put light in our box. So, our first requirement was that we wanted energy in the box, and we've done that in the form of light. The second requirement is that the energy needs to stay inside of the box. How do we do that? Well, let's envision that our box has perfectly reflecting mirrors, so that the light inside bounces around indefinitely. Now, to make things simple, let's imagine that we have only one photon in the box, and it's only bouncing along one direction. A photon carries both energy and momentum, related by the equation E equals pc. P is the value of momentum, and c is the speed of light. When light reflects off of a surface, it transfers some momentum to that surface, such that the total momentum of the incoming photon plus the reflected photon exactly balances the momentum transferred to the surface. As the photon bounces back and forth inside of the box, it will transfer momentum, first to one side and then to the other. Because the photon is transferring the same amount of momentum to both sides of the box, the momentum perfectly cancels out. The photon doesn't transfer momentum to the box, so the momentum of the box doesn't change. Well, so far, so good. When our box is at rest, it tends to stay at rest. But that's just the easy part. So the question now becomes, what will happen if we push on the box? Well, as we push the box, it will begin to accelerate. If we imagine that we start pushing right when the photon bounces off of one of the sides, then by the time the photon reaches the other side, the box will now be moving with a non-zero velocity. Now, light is a relativistic object. This means that it is sensitive to the speed of both the emitter of the light as well as the receiver. The effect of this is that a moving surface perceives both the incoming and reflected photon as having a different energy and momentum than what it had when the surface was at rest. This process is called relativistic Doppler reflection, related to the simpler concept of relativistic Doppler shift. In cases where a reflective surface is moving toward the incoming light, both the incoming photon as well as the reflected photon are perceived as having higher energy and momentum. Thus, the total amount of momentum transferred to that surface is higher. We call this blue shifted because blue is at the more energetic end of the visible light spectrum. In cases where a reflective surface is moving away from the incoming light, the process is reversed and a smaller amount of momentum is transferred to the surface. We call this red shifted because red light has much less energy than blue light. So when we push the box, the photon inside transfers blue shifted momentum on one wall, and redshifted momentum on the other. These two contributions of momentum no longer cancel out. The blue shifted momentum outweighs the red shifted, so we have a leftover component of momentum transferred to the box. In other words, the light inside of the box generates a force that resists pushing on it. That's inertia. And the only thing required to create it is energy that is trapped, which experiences Doppler shifts. Our next job is to drop the box. In order to do this, we must understand how light behaves in a gravitational field. Now, this is actually much more complicated conceptually, but fortunately, it's very easy to describe. Einstein discovered that a gravitational field will influence the energy and momentum of light. Light traveling toward a gravitational source will be blue shifted, while light traveling away from the source will be red shifted. In our case, that means light traveling down has more energy and momentum than light traveling up. Inside of our box, the photon is transferring blue shifted momentum to the bottom surface and red shifted momentum to the top surface. Once again, these contributions of momentum do not cancel out. Thus, the light inside of the box is actively generating an overall force pushing downward. In order to progress this mission, let's examine some important relationships regarding energy, momentum, and mass. So far, we've seen two very important equations regarding energy. The first is E equals mc squared. I've been trying to make clear each time we've talked about this equation that it specifically represents the energy of an object at rest. Such an object would have zero momentum, so one way to say it is that this equation represents the energy of an object which carries mass, but no momentum. We've also seen the equation E equals pc when discussing photons. This equation represents the energy of an object which carries momentum, but no mass. When described in this way, we can see that these two equations are peers of each other. So how do we describe the energy of an object which carries both mass and momentum? The answer comes from relativity theory, and it is E squared equals pc squared plus mc squared squared, and that's a lot of squareds. Well, this relationship, as the sum of squares, is a Pythagorean relationship, which is the same kind of relationship used to describe the geometry of a right triangle. This implies that momentum and mass are somehow orthogonal to each other. But how can that be? Momentum is a vector, which points in an associated direction, where mass is a scalar, which does not. How could directional momentum be orthogonal to directionless mass? If we remember our initial example of a photon bouncing inside of a box, the mass was determined to be the consequence of averaging over multiple energy transfers, which were oriented in opposite directions, such that the momentum canceled out. What this triangle relationship is really telling us is that the momentum that cancels out is orthogonal to the momentum that doesn't cancel out. In order to visualize the geometry of this relationship between mass and momentum, let's take our imaginary box and stretch it out to create a long hallway. We can now describe the motion of the photon in terms of two orthogonal components. The photon might possibly bounce back and forth between the walls without actually progressing down the hallway. Alternatively, we might direct the photon so it moves down the hallway without bouncing between the walls at all. We can associate mass with the first case of bouncing between the walls and momentum with the second case of traveling down the hallway. In the general case, we may have components of both kinds of motion. This can possibly be represented as a photon traversing a zigzag path as it moves down the hallway. To understand this general case, we can think of the photon as spending some of its time traveling down the hallway and some of its time bouncing back and forth between the walls. Some of the energy is contained and some of the energy is not. The right triangle, which represents the relationship between momentum, mass, and energy, is a similar triangle to the one that we can see in the zigzag motion of the light. Now, so far we've described this general momentum containment mechanism which generates mass in terms of particles, where we talk about things like collision or momentum transfer, but earlier on I made the statement that I believed that all properties of particles were just idealizations of certain classes of wave behavior, including the property of mass. The fact that we usually don't think of waves as carrying mass is actually a positive thing here, since we're pursuing this mission of getting mass from no mass. But can we justify this claim? is there any premise at all that we can use as a starting point to describe how waves might carry mass? Well, so far we've shown that mass is very literally energy that has been contained, which is concisely represented by the equation E equals mc squared, which is the energy of a massive object at rest. We've known for centuries that waves can carry energy, but on the surface it doesn't seem meaningful to talk about waves as being at rest, because they're always moving. Well, actually it turns out that there is a meaningful way. There is a class of wave motion called a standing wave, which, as opposed to a traveling wave, represents oscillations that are not moving. This idea of a standing wave will become our starting premise for describing mass in terms of waves instead of particles. The great thing about using waves to describe mass is that we've spent centuries developing these deep formalizations for describing and understanding waves and wave behavior starting from first principles. On the other hand, when it comes to particles, we've historically relied on colloquial and axiomatic definitions as our starting point. In other words, we understand the fundamental properties of waves way better than we've ever understood particles. To proceed with the wave-based analysis, we will return to the light bouncing down the hallway. Except, instead of thinking of the light as a particle bouncing off the walls, let's now think of it as a wave, which extends to fill up the entire hallway. In wave analysis, this configuration of a wave moving through a confined space like this is called a waveguide, and the process by which the wave is confined to the waveguide is analytically understood in terms of what we call boundary conditions. Now, waves have a frequency and a wavelength. We often parameterize these values in terms of omega and k. For freely propagating waves out in the open, these parameters have a very simple relationship to each other. However, when a wave is inside of a waveguide, that relationship becomes a bit more complicated. Here's an example of what we call a dispersion relationship, relating the frequency and the wavelength of the wave inside of the waveguide. Now, the dispersion relationship can be derived directly from the wave equation, as well as boundary conditions. Now, the first term on the right-hand side is associated with the traveling wave component that moves down the waveguide. While the rest of the stuff on the right-hand side we'll talk more about later, but for now, let's just say it is representative of the standing wave component. We can observe again the sum of squares, which represents triangle geometry, similar to what we were previously discussing. This might motivate us to attempt to transform our equation into something involving energy. Unsurprisingly, we're going to once again consult Albert Einstein to help us out with the next step. Albert Einstein was awarded a Nobel Prize for his work involving the photoelectric effect, where he determined that photons transfer energy in quantized units. The primary energy relationship for a photon is E equals h bar omega. In the same year he published the photoelectric effect, he also published a paper discussing the details of Brownian motion, where he defines a relationship between momentum and wavelength, P equals h bar k. If we multiply our dispersion relationship by h bar squared, we can employ these two fundamental relationships in order to get an equation that describes the energy and momentum of a single photon. Now, comparing this with the equation relating energy to momentum and mass, we see that the mass portion must be equal to the standing wave terms. So we now have a very straightforward mathematical confirmation that we can directly associate mass with the standing wave. Now, these terms look kind of complicated, so let me describe what's going on here, and maybe you'll be convinced that this really does represent the standing wave. The parameters a and b represent the length for each dimension of the cross-section of our waveguide. The parameters m and n are whole numbers that represent the number of half wavelengths in the standing wave spanning each of those dimensions. We can tweak those numbers in order to represent different standing waves, so the m and the n really are representing an entire class of possible standing waves, which we generally refer to as modes. The best way to understand this is to envision that the standing wave forms a kind of grid which contains a certain number of oscillating nodes and stationary antinodes. The parameters m and n define how many cells of this grid we have in each dimension. Now, if we want to simplify this expression a bit, we can recognize that if we take the ratio m over a and invert it, then we've divided the total length into several equal units. If m represents the number of half wavelengths, then this unit is just the size of a single half wavelength. We can replace the ratio m over a, as well as n over b, with the inverse half wavelengths corresponding to each of those dimensions. We still see a sum of squares here, this time between the inverse wavelengths in each of the orthogonal directions. We can envision some overall inverse wavelength which lies on the hypotenuse of some right triangle. Let's call this wavelength the standing wavelength, as it is indicative of the overall standing wave. After making this replacement, the equation reduces quite a bit, and we are left with a simple relationship expressing the mass of the wave in terms of the standing wavelength of the wave. If we invert this relationship, what we discover is the well-known formula for the Compton wavelength. Now, in the early days of quantum mechanics, it was discovered empirically that all massive objects exhibit a wavelength defined exactly as shown here. In this case, we have derived the expression from first principles without invoking any kind of particle properties at all. This is significant because while we already knew from Compton that mass implied waves, we can now complete the picture and say that waves imply mass. We now have the necessary and the sufficient conditions required in order to establish an identity. What we found is that the Compton wavelength is identical to the standing wavelength. If we generalize this idea, we infer that for any wave that carries energy, we can discover a standing wavelength component. Identifying this standing wavelength directly with the Compton wavelength will allow us to determine the mass carried by that wave. So here's the really great thing about what we've just discovered. The idea of creating or manipulating mass seems mysterious and completely unapproachable when you think of mass as some axiomatic property of particles. But if mass is just a consequence of standing waves, well, we've been creating and manipulating standing waves for a really, really long time. At least as long as we've been making music. Each musical note we create corresponds to a standing wave, usually on a string or in a pipe. Part of the genesis for the theory of waves was an effort to better understand how to make music. So, surprisingly, the fact that we are a musical species honestly really prepares us to start opening the door to the idea that we can actually design or manipulate mass. It's possible that we've been doing it all along whenever we pluck a string. One place where this concept is abundantly apparent is in the construction of nanocircuits, where the size of the wire becomes comparable to the size of the electron. What folks working in this field have discovered empirically is that when you very tightly confine an electron, its inertia actually changes, such that forces act on it as if it has a much larger mass. This ends up making quite a difference in how they design the circuits because the electrons move differently and respond to electric fields differently when they have more mass. Scientists have associated this extra mass with the dispersion relationship, just like we've done here, which they refer to as effective mass. Now, in many cases, it isn't clear to me that scientists think of this as real mass, just some kind of effect that mimics mass. But I believe that it is absolutely real mass in every dynamical sense, from the abstract source terms all the way up to our most naive macroscopic experiences associated with mass. And if that's really the case, then we are already designing systems that create and modify the mass of physical objects in a non-trivial way. This is really exciting. A proper understanding of how waves can carry mass means we can take our long history of studying waves and apply it directly to our study of mass and inertia. We can now create and study masses with all sorts of exotic properties. We can create masses that have differing values of inertia depending on the direction that the force is applied. We can create masses that have a different dimensionality, where instead of confining the wave to a narrow tube, we confine it to a large extended plane. We can even create negative mass objects. But my absolute favorite idea is to think about how we can design a system where the mass of an object changes. Understanding this kind of system could unlock new methods of propulsion and thrust. And exploring that idea will be the topic of my next video.